All right, guys, I got 3:30, so let's go ahead and get started with things. First off, any questions about lab for tomorrow and expectations there? We're starting a new lab, remember that. So you guys should all have the procedures and you should have the stuff written into your notebook that you normally would prior to coming to lab. And also remember, you're going to get a short lab quiz tomorrow, first thing when you come in. That'll happen every time we come into lab. Then the last thing, of course, is I want your yellow pages for the calibration of the burette. All right. Other than that, any comments, questions, anything we got to go over regarding lab? Everybody good? Okay. All right. Let me go over to whiteboard here. And over to notes. All right, so I have some quant notes here, or skeletal notes that are basically I'm ready for us to look at here. So let's go ahead and start with that. All right, so just make sure everybody's hearing me okay. Just somebody chime in and say, yes, I can hear you, just because I haven't heard from anybody.
Yep.
Good. Right. Just checking. I always like to make sure of that. Sometimes I can get thrown off and never know I got thrown off. Okay, good deal, guys. So what we want to do is we want to build on a specific kind of equilibrium process. So if you recall last Wednesday, we spent the majority of the time talking about chemical equilibrium, right? So we talked about how we can describe a reaction at equilibrium according to the law of mass action. So we could build an equilibrium expression based upon equilibrium concentrations for a given reaction under a certain set of conditions. So what I want to do is build out on that today and talk about a very specific kind of equilibrium constant expression. So what we're going to find is that when we talked about those K values, those big K values, those equilibrium constants for any given reaction, I called that last time a KEQ for an equilibrium constant. But what we're going to find out is that there are lots of different types of equilibrium constants depending upon the kind of reaction we're talking about. So for example, if we're doing an acid or base reaction, we'll have a Ka or a Kb. Those are what we'll call the equilibrium constants for those kinds of reactions. Likewise, in this case, we want to talk about one called a solubility product, because here we're talking about an insoluble species. Okay, so think back to bonding. And this kind of ties into the lab we're going to start tomorrow as well. So the timing is good here. So we can write a reaction, and the way we do it back in bonding is something like this. Let's say we want to write a reaction to show two ions in solution coming together to form an insoluble species, right? So I could do something like this and see if you guys were to remember your solubility rules here. I could have barium ion, which I could introduce as, say, a soluble barium salt like barium chloride. And I could let that react with sulfate ion, which again, I could introduce into solution with some soluble salt like, say, sodium sulfate or ammonium sulfate or something like that. And then based upon our solubility rules, and what we're doing is we're generating essentially a net ionic equation here, because I've gotten rid of all the spectator ions, just keeping things simple, is that I could now show this as these two ions coming together to form the insoluble species barium sulfate, the ASO4. Okay, and you'll probably remember that that's one of those insoluble compounds that you can make. So if I introduce the barium ion in solution to the sulfate ion in solution, they'll find each other and they'll form a precipitate, which forms out on the bottom. And I think the barium sulfate is a white precipitate you would see forming on the bottom of the beaker. Okay, so this is the way we think about this back in bonding. And of course, we also know that we can calculate how much barium sulfate precipitate we form through a limiting reactant calculation, right? So if I knew that the barium ion was the limiting reactant and I knew how much of it I had, I could use simple stoichiometry to get myself to grams of barium sulfate, right, through a mole bridge. So we all know how to do that. All right, but now we have to think about this as an equilibrium expression. So now we have to think about when we form the barium sulfate product, what's really happening is that some of it actually redissociates back to the ion forms. The reaction doesn't really go 100% to the right. okay? And this is where this idea of KSP comes into play. Now, if you could go in the lab and do this, right? And you could do this experiment, and you could actually isolate and weigh the barium sulfate based on the amount of, say, limiting reactant that you actually know you put in there, and you get about 100% recovery. So in other words, that's another way of saying that this reaction really goes almost 100% to the right. So if I were to write a K for this reaction in terms of the law of mass action, remember what the magnitude of K tells us. It tells us how far to the left or the right the reaction goes and ultimately ends up at equilibrium. So if this reaction ends up making a whole lot of precipitate and leaving essentially no limiting reactant behind, what does that tell me about the K value for the reaction here as I've written it? Does it have a big K or a little K?
It's gonna have a large K.
Yeah, really big K. Okay, so this reaction, because we can actually do it and isolate the barium sulfate and weigh it and check a percent recovery, has a really large K. And that's generally true. If I'm talking about forming a precipitate, if I wanted to write this in terms of law of mass action and calculate an equilibrium constant based upon equilibrium of ions left in solution, I'd have a really big K. All right, so here's the deal. When we actually talk about these kinds of reactions, we do it in terms of this thing called a KSP, which is a solubility product. Now, here's the oddball thing. Usually we think about this in terms of forming the precipitate. But in fact, when we talk about a KSP, we're talking about the reverse situation. It's as if I were going to take a bunch of barium sulfate solid that I already had, say from the shelf in the stockroom, throw it into some water, and let the system come into equilibrium. So in other words, I'm letting the reaction dissociate back away from the salt toward the ions in solution. So the KSP reaction is really this reaction in reverse. Okay, so I would write it like this. Sounds counterintuitive, but that's just what we do. Okay, use our double-headed arrow because we're talking about an equilibrium. So I get barium 2 plus, that's an aqueous solution. And of course, I get a sulfate ion. Stoichiometry tells me it's all 1 to 1 to 1. Now, if the reaction I wrote above has a large K, what do you expect this reaction to have? A big K or a small K when I write it in reverse?
Small K, inversely proportional.
Yeah, you got it. It's a small K. And we would know that because the K for the second reaction is just 1 over the K for the first reaction. And 1 over a very large number gives us a very small number. So what this tells me is that KSPs have a tendency to be very small numbers. So this reaction is governed by this KSP. All right. So now, could we use the law of mass action to actually write out an equilibrium expression for this? In other words, KSP in terms of the concentrations of the species in the balanced chemical reaction equation? Sure. Remember how it works. The equilibrium constant, KSP, is equal to the concentration of the product concentrations at equilibrium divided by the reactant concentrations at equilibrium, all raised to their corresponding stoichiometric powers. Okay, so I'm talking about a molar concentration of barium 2 plus at equilibrium. Remember, these are equilibrium concentrations times the sulfate ion concentration, and these are all raised to the first power because the stoichiometric coefficients are 1. And then we might be tempted to put BaSO4 down here at the bottom. But what do I know about the barium sulfate? Notice its state. It's a solid, right? Now, do we remember anything about solids and equilibrium constant expressions?
They aren't included.
They're not included. So solids don't show up. So I really have to take the barium sulfate out, right? So really what I've got is just the product of those two ion concentrations at their equilibrium values. And those are all equal to the KSP. Now, the nice thing about this is these are all tabulated values, right? I can go to tables and look them up. So the KSP for barium sulfate dissociation at 25 degrees Celsius turns out to be, and these are all in your textbook, 1.1 times 10 to the minus 10th. Oh, that's a pretty small value, isn't it? So it tells me that this reaction, as I've written it, doesn't go very far to the right. And that tells me that it favors the formation of the precipitate, and that's exactly what we said to begin with. Okay, so does that make sense? Everybody see how I got at that and why it makes sense that it ought to be a small number? So I'm talking about the dissociation of the precipitate as opposed to its formation.
Yep.
Okay, good. So here's the thing. Once I've got a balanced chemical reaction equation, and if I know the KSP value for it, like I said, I can go look that up in a table. Now I can start to actually work problems, okay? So let's take a look at example 1 here, and I'm gonna give you a minute to write it down, and I'll read it out as you do that. What I wanna do is calculate the equilibrium concentration of sulfate ion when barium sulfate comes to equilibrium in an aqueous solution. So it's exactly what we just talked about. I'm gonna go find some solid barium sulfate in the stockroom. I'm gonna throw it in some water at 25 degrees Celsius and let the system come to equilibrium. Now, what I wanna know is that once we've achieved equilibrium, what's the equilibrium concentration of the sulfate ion in there? Okay, that's what I wanna know. So would you expect that to be a big concentration or a small concentration when the system comes to equilibrium, just to kind of think about this in terms of the KSP? You're gonna make a lot of sulfate or very little sulfate?
Very little.
Very little, yeah, because the KSP says the reaction's not gonna go very far to the right when I write it as the dissociation. So you're exactly right. So I'm gonna start by just rewriting the KSP reaction, right? So we're talking about, by definition here, the salt dissociating in water. So I'm gonna write my barium sulfate here. That's a solid. And I'm gonna let it come to equilibrium with its 2 ions. So I'm gonna make some barium ion. And I'm gonna make some sulfate ion. Okay. Now, here's what we have to do. And we're going to do this pretty much every time we work an equilibrium problem. And if you guys ever did this in high school, like as part of an AP course or something like this is going to be old hat for you. But if it's new for you, get used to it because we're going to be doing it a lot. And this is also something you're going to spend a lot of time doing in the dynamics course that you're in. So what we're going to do is we're going to use this thing called an ice table to get to equilibrium concentrations. Anybody ever seen an ice table before?
Yep.
I'm sure a few of you have. Okay. And we'll go over it. And it works for any kind of equilibrium problem. Doesn't just work for KSPs or whatever else. It works for any kind of equilibrium problem we want to throw at it. Okay. So here's what it corresponds to. The I stands for initial. So this is going to be a starting concentration if we know it. Okay. C stands for change. It's the change the reaction has to go through to get from an initial set of conditions to equilibrium. And then finally, E obviously is going to be equilibrium. Okay. So initial, change to equilibrium, and equilibrium. That's what ICE stands for. All right, so what we're going to do is we're only going to worry about things that actually show up in the law of mass action. If something doesn't show up, I'm going to put a big X through the table, so I'm not tempted to put something in there. So is there anything in there I can X out right from the get-go?
The BOSO4.
Yeah, the barium sulfate. So I'm just going to put a big X there. I don't care what IC or E are for that because it never shows up in the law of mass action, and that's my algebraic expression I'm going to work with. Okay. So now initially, before anything has happened, do I have any barium ion in there?
Yes.
No.
I'm hearing different answers here. Think about what we're doing. I'm taking barium sulfate solid and I'm throwing it in some water. Okay, so before the reactions had any chance to happen, do I have any barium ion in there yet?
No.
No.
No, I haven't had a chance for the dissociation to happen yet. So I'm going to put 0 up there. And obviously these are molar concentrations, so these things have units of molarity. Do I have any sulfate ion in there?
No.
No, I don't. Haven't made any yet. Okay, so now we get to the change part. This kind of becomes our variable. But the first thing I ask myself is, which way does the reaction have to go to get to equilibrium? Does it have to go to the left or to the right?
would have to go to the right, correct?
Yeah, it certainly would, because all I've got is barium sulfate. I haven't made any ion yet. And to get to equilibrium, I got to make some ion, right? So this tells me that I have to let the reaction shift from left to right to get to equilibrium. Now, do I know off the top of my head, or do I have any way of knowing with the information given in the problem how much barium ion am I going to make, or how much sulfate ion I'm going to make? No, there's nothing in the problem that tells me that. That's an unknown. So we can give the unknown a symbol like X or Y or whatever we want to call it. Okay, so I'm going to put an X in here under the barium ion, and I'm going to put an X under sulfate. Now, something to keep in mind when you're dealing with these kinds of tables is that if you have a stoichiometric coefficient, that follows down. So for example, if I were making 2 sulfates for every barium, okay, I'd put a 2x there for sulfate. But since I've got a 1-to-1 correlation there, I just use an X and an X. Okay, so be careful of that, because sometimes you don't have 1-to-1 stoichiometry. Now, the E line's really easy. All you got to do is you add the I and the C downward. So 0 plus X gives you X, right? For the sulfate, 0 plus X gives you X. So X's turn out to be my equilibrium concentrations for both the barium ion and the sulfate ion. But now what this allows me to do, so you might look at this and say, well, we didn't really accomplish anything. But in fact, we did. Because ultimately what I'm trying to do is figure out what X is, right? Because what does X represent? X represents the equilibrium, or E, concentration of the sulfate. That's what I got right here. So if I can generate an algebraic expression and solve it for X, I've got the equilibrium concentration of the sulfate in the solution. Everybody see that? Now I just need an algebraic expression with X in it. Do I have that? Yeah, I do have that. Because remember, I've got that wonderful thing called the law of mass action that I can write, okay? And just reminding myself what that looks like, I can say that KSP is equal to, oh, what was it? It was the concentration at equilibrium of the barium ion, just to remind myself, times the concentration of the sulfate ion, also at equilibrium. And all that's equal to what? Was it 1.0 times 10 to the minus 10th, or 1.1 times 10 to the minus 10th? Oh, so those are equilibrium concentrations. Do I have another name for the equilibrium concentration of barium ion or sulfate ion? Yeah, it's X in the table, right? So what am I going to do? I'm going to let that be X. I'm going to let that be X. And I'm going to multiply them together. And when I do that, I get X squared. And that's equal to my KSP value, which, recall, I can go look up in a table. Can I solve that for X? Sure, just take square root of both sides, right? And if I do that, I get 1 times 10 to the minus 5th or something like that. I think that's what it turns out to be, to sig figs. And remember, that's a molarity. And it's the molarity of the sulfate ion. It's also the molarity of the barium ion. And that makes sense, because if you have a dissociation of barium sulfate, you're getting 1 barium per dissociation. You're also getting 1 sulfate per dissociation. Okay, so does everybody see how I could sort of set up an ICE table and use that ICE table to develop an algebraic expression in terms of the law of mass action that I can then solve for an equilibrium concentration? So it's just a tool that we use. Okay, so everybody see what I did there? Any questions, especially for folks who haven't seen this kind of setup before? Does it make sense? Anything we need to elucidate here? Okay, good. So here's the next thing we have to think about. So that's a real easy way to get at an equilibrium concentration of an insoluble species in solution. But we have this other business called saturation and ion product. Now, what ion product refers to is sort of a combination of 2 soluble ions that we actually have in solution. And based on our knowledge of those concentrations, we should be able to predict whether or not we form a precipitate or not. Okay, so what is the ion product? Well, the ion product is essentially the same as the law of mass action, but it's for whatever concentrations of the ions we've actually got in solution, as opposed to equilibrium concentrations. So in other words, I can think of it as concentrations prior to equilibrium, okay? So if I write an expression for Q, which is the ion product, it looks like the same expression as I would use for the law of mass action, except that I may not be at equilibrium. So in this case, using the prior example, Q would equal to the barium ion concentration, again, not necessarily at equilibrium, times the sulfate ion concentration, again, not necessarily at equilibrium, okay? And if I knew what those, if I wanted to think of it as starting ion concentrations were, I could get an ion product and calculate it, okay? So here's the thing. Based upon what that ion product is, I can make a comparison between Q and KSP and make a prediction as to whether I'm going to form a precipitate or not. So if you think about it, I've really got three options here if I compare these things. I could have a situation where my Q or my ion product is less than my KSP. I could have a situation where my Q is greater than my KSP. Or I could have a situation where my Q is actually equal to my KSP. Okay, so each one of these means something different. So let's think about it. If my Q is less than the KSP, that means I don't have enough of one or the other or both of the ions to form a precipitate. Okay, so in that situation, I've got a solution that is unsaturated. We all know what saturation means, right? So both ions are present in the solution, but not in quantities high enough to form the precipitate. That's what an unsaturated solution is. Think about, when you do saturation studies of like sugar and water, right? You can add sugar to water and it dissolves, and you don't necessarily see any solid sugar sitting on the bottom. That's an unsaturated solution. But then if you oversaturate the solution, what happens? Well, you got sugar water on top because you've put as much sugar in the solution as you possibly can. But now you've got an excess of sugar that you can't dissolve. So where does it end up? Well, it ends up as a solid on the bottom of the beaker. And what's the saturation point? Well, that's when you've got just enough sugar in there to fully dissolve and not have any sitting on the bottom of the beaker. Everybody's done that in like 7th or 8th grade or wherever, right? So you know what I'm talking about there. So if I have a Q that's greater than a KSP, well, that means my KSP requirement has been met. It's actually been overmet. So this is a situation where obviously I'm oversaturated and I obviously see a precipitate on the bottom of the beaker. Okay, so in other words, precipitate forms. All right. But then what if my Q is right at my KSP? Well, that's the point of saturation. That's the tipping point. Okay, so I may not actually see any precipitate on the bottom, but if I went 1 iota beyond that in terms of concentration of one or the other or both of the ions, I'll see a precipitate. Okay, so KSP really is that tipping point between being unsaturated and oversaturated. All right, that's what KSP really means. Okay, so we can use Q as a means of kind of calculating in advance whether or not we have a precipitate or not, just by comparing my given Q to my KSP. Okay, so that's what I mean by unsaturated, oversaturated, or right at the point of saturation. Does that make sense to everybody? Any issues there? All right, well, let's just take a look at what I mean by this. So we can apply this to an example here. So this is example number 2. Again, I'll give you a moment to write it down before we get into it. So what it says is that a solution already contains 0.0256 molar sulfate ion. So the question now becomes, what minimum concentration of barium ion do I need to add to that solution to get a precipitate to form? In other words, I got to get to that tipping point, right? So the minimum concentration is defined by that situation where the Q is actually equal to the KSP. Because if I go 1 iota beyond that, I got precipitate. Okay, so that lets me calculate my tipping point. Okay, so the nice thing about this is I can go right to my KSP expression here. Right, and I know what it is. It says that the concentration of the barium ion, this is just my law of mass action, times the concentration of the sulfate ion, is equal to a KSP value, which I know that's 1.1 times 10 to the minus 10th. So this represents an algebraic expression, right? Because I know what the sulfate ion concentration already in the solution is. That's given to me. So I'm just going to write that in 0.0256. So the question now is, how much barium ion do I need to introduce to the solution to get the precipitate to form, or more specifically, hit the point of saturation? Okay, so basically I have to add whatever amount of barium is needed to generate a molar concentration that satisfies that algebraic expression. So all I'm going to do is I'm going to solve for the barium ion concentration. So that's going to equal to my KSP, which is 1.1 times 10 to the minus 10th, divided by my sulfate ion concentration, which is 0.0256. Okay, I'm just going to leave molar out here because we know that we end up with a molar concentration, and we also know that K values don't carry units, but we know we got to end up with a molarity here. Okay, so I can actually work this out. And 2 sig figs, I get 4.3 times 10 to the minus 9th molar. Not very much, right? And that's going to be barium. Okay, so that's the minimum concentration of barium ion I need to have in that solution to get to the saturation point. If I go 1 iota beyond that, I've got a visible precipitate. Okay, and again, that tiny number here speaks to the fact that I have a very tiny KSP for this thing. Okay, so in other words, I'm thinking about forming the precipitate. It's very easy to do. I don't need a lot of ion in there to make that happen. All right, so everybody kind of see how that relates back to what I was talking about up here in terms of an ion product. Any other questions? All right. So let's talk about one other thing here. And this kind of plays into what we're doing in the lab. It's called the common ion effect. Now, the common ion effect is really nothing more than Le Chatelier's principle employed. Okay. You guys know Le Chatelier's principle? I don't know Le Chatelier's principle. Hell, I don't even know where he went to high school, and he lived 300 years ago. Come on, laugh, people. You're a tough crowd.
That was a good one.
Thank you. All right, so anyway, here we go. Common ion effect, an application of Le Chatelier's principle. Now, remember when we talked about Le Chatelier's principle last time, what we said is that we're going to apply some sort of a stress to a system at equilibrium, right? And the system, the reaction, is going to respond to that stress in whatever way it needs to get back to an equilibrium condition. Okay, so we talked about, for example, if I want to drive a reaction further to the right, I could add more of a reactant to make that happen. So essentially what I'm doing is I'm generating a Q here, and then I'm forcing the Q to go to K by shifting the equilibrium. Another way of doing the same thing is I could remove a product and force the reaction to go further to the right. Okay, and we said that, like when we're making a precipitate, like in the quant lab, that's a really important thing to do. So we want to kind of make sure that we have lots of our excess reactant in there to keep driving that reaction as far to the right as I possibly can. All right, so that's sort of an application of it. So let's just think about barium sulfate just to begin with here, and then we'll talk about applying a stress to it. So this is, again, the same reaction or situation that we've been talking about all along here. Barium sulfate, this is defined by a KSP, and we're going to let that dissociate to give us barium ion. and sulfate ion. Okay. Now, if we go back to example number 1, what we see is that if we throw some solid barium sulfate in there and let it come to equilibrium at 25 degrees, we know that we're going to end up with a mixture of barium ion and sulfate ion in there. And we calculated what their concentrations would be. It was 1.0 times 10 to the minus 5th molar, and also 1.0 times 10 to the minus 5th molar, right? Because I make equal amounts of both. Okay, and that comes from example number 1. Now, here's the question. If I throw some extra barium ion in there from another source, like maybe soluble barium chloride, I'm applying a stress to this by adding a product, right? What's the equilibrium going to want to do? Which way is it going to want to shift?
Back to the reactant.
Yeah, it's going to shift back to the reactant, right? So in other words, I'm kind of generating a Q here and I'm comparing a Q to my KSP, right? So in this situation, what's happened, right? I made my Q bigger, didn't I? Because I added more barium ion. And I want to get back to my KSP. So what ends up having to happen is I've got to end up allowing those ions to come together to form more barium sulfate to get me back to equilibrium again. Okay. So that would be a way to form more precipitate if I wanted to do that. All right. Everybody kind of see the idea there? So adding, in this case, a product shifts the equilibrium back to the left or toward the solid side. That's applying a stress to my system, and the system will respond in some way or another to relieve that stress and get back to its original equilibrium position. So that's a good example of that. So let's look at what might happen in a situation like this. So this is kind of example number 3, and I'll show you a few shortcuts here that we can assume, but basically it's the same situation. In example number 3, I'm asking, what's the sulfate ion concentration in an equilibrium mixture of barium sulfate when the mixture happens to be made 0.2 molar in the barium ion by adding, say, solid barium chloride? Okay, so what I'm doing is I'm letting a system come to equilibrium, and then I'm dumping a whole bunch of barium ion in there. Okay, so it's exactly the situation that I showed up here in this little example, right? So what ended up happening? Well, I end up using up some of the sulfate ion as well as some of the barium ion and pushing that reaction back to the left toward the solid. So the same thing's going to happen down here in this example, okay? So what we're going to do is we're going to set this up according to an ice table, just like we did in example number 1. So let's write the reaction out exactly in terms of a KSP reaction here. Okay, and I know what I'm going to make. I'm going to make some barium ion. I'm going to make some sulfate ion, both of these obviously with AQs under them. I'm going to do an ice table. All right, now there's a nice little shortcut we can make here. Okay, we know that if we start out with just barium sulfate in solution and let it come to equilibrium, we're really going to have initially some barium ion and some sulfate ion in there, right? And we said what they were. 1 times 10 to the minus 5th molar. So really tiny amounts, right? Now, because the amount of barium ion that I'm going to be tossing in here is really big compared to 1 times 10 to the minus 5th, what I'm going to do after I X out all of my barium sulfate, because we know that doesn't show up in the law of mass action, is I'm going to hedge a little bit. And rather than putting 1 times 10 to the minus 5th, I'm going to let the sulfate ion concentration be 0. And I'm going to let the barium ion concentration be equivalent to whatever I added here. So in a sense, what I'm doing is I'm setting this up as a new equilibrium without worrying about that tiny pre-equilibrium that we set up before. So I'm saying I'm just going to set up a set of initial conditions that suggest that this reaction is coming to equilibrium without ever having seen an equilibrium prior to this. In other words, it's like I'm going to throw some barium sulfate in at the same time as having 0.2 molar barium ion thrown in, and we're going to just say we've got no sulfate ion there to begin with. Well, it just makes everything easier, okay? So if I look at this as I have it written right now, which way does this reaction have to go to get to equilibrium? As I have it written with my I values in there, which way do I have to go? That's always the first question we ask ourselves is which way does the reaction have to go to get to equilibrium?
To the left.
Okay, here's my question back to you. Can it go to the left if I have no sulfate in there?
Yeah, 0.2 times 0 is 0, so we have to go to the right so we produce sulfate.
You got it. You got to make some sulfate because you've got none in there to begin with. In other words, if you calculated a Q for this reaction right now, based on those initial concentrations, what would the Q equal to? It would be 0 times 0.20, which is 0, right? So what have I got? I've got a situation where my Q is less than my KSP, even though KSP is really, really tiny, right? And if Q is less than KSP, which direction do I have to go to get to equilibrium? I got to go to the right because I want my Q to be equal to my KSP at equilibrium, right? So I've got to go right. So that's always the first thing I ask myself when I set up something like this. Which way do I have to go? In this case, it's fairly obvious because I got to make some sulfate. But if it weren't obvious, I could calculate a Q and compare it to a KSP. If the Q is less than the KSP, I go to the right. If the Q is equal to KSP, I do nothing because I'm already at equilibrium. And if my Q is greater than my KSP, I know the reaction goes left. Okay, so it never hurts to, even if you're in your head, just calculate a Q and let that decide for you which way the reaction's got to go to get to equilibrium. Okay, so now the change, obviously left to right, is I'm going to make X of barium and I'm going to make X of sulfate. Why is it X? Well, because they have a 1:1:1 mole ratio amongst all three of those things. So for every 1 mole of barium I'm making 1 mole of sulfate. So that's why I have a 1 in front of the X. Add down to get my E line. Plus X, right? And then 0 plus X is just X. Everybody see what I did there? So now I need an algebraic expression, right? So I'm going to plug everything back into the law of mass action, just like I did before. So let's remind ourselves of what the law of mass action looks like for this. It says that KSP is equal to my equilibrium concentration of my barium ion, comes from my E line, times the sulfate ion concentration also at equilibrium. So that comes from the E line. That's equal to, what was it, 1.1 times 10 to the minus 10th. That's my K value that I looked up in the table. All right, plug it all in. Barium ion. Looks like it's going to be 0.20 plus X from the E line. And the sulfate is the X from the E line, and all that's equal to 1.1 times 10 to the minus 10th. Okay, so how do I solve that equation for X?
Algebra, and then you can use the quadratic formula since it's a 3 polynomial. Well, it's a binomial. It's simple. Yeah.
Yeah, just distribute the X through, right? So you end up getting X squared plus 0.20X, and all that's equal to 1.1 times 10 to the minus 10th, right? Then you rearrange it. And then I say minus 1.1 times 10 to the minus 10th is equal to 0. And then I apply the quadratic equation. Okay, remind me of the quadratic equation because that's also a 1 there. So that's my A value, that's my B value, that's my C value, right? Okay, so let's see, I haven't used it in a while. I always have to remember it. So it says that X is equal to, what is it, B squared minus the square root of, what is it?
No, it's X minus X equals negative B plus or minus the square root.
B squared minus 4AC.
Yeah,
right?
Divided by 2A.
That sounds right. Thank you. I don't have it written down, and I always have to remember it. Okay, so everybody knows what to do here. You plug your values of A, B, and C into the equation, and you end up getting 2 roots out of it, right? And one root will actually make sense when you plug it back into the law of mass action, and the other one won't. So oftentimes you'll get a positive root and sometimes you'll get a negative root. And you can't have a negative concentration for X. So usually, you can throw that one out. Okay. So that's the way to get an absolutely correct algebraic answer for this. Okay. But as you can see here, it takes some time to go through the distribution, rearrange the equation, and plug everything into the law of mass or into the quadratic equation, get your two roots, and then decide which one to use. Okay. It's a pain in the ass. I'll be honest. I don't like to do it. Is there a way around it? Well, it turns out that in some cases there is. Okay, so what I want to do is go back up here to my original equation that I have here. Okay. That I generated before I did any rearranging here. So what it's telling me is that the product of those two things has to equal to 1.1 times 10 to the minus 10th, which is really a very tiny number. Okay. So what does that suggest to us? Well, it tells us that X is probably going to be a pretty tiny number. All right, so as a result of that, notice that in this first term, I'm adding X to 0.20. Now, if I have already established that X is probably going to be a pretty tiny number, does it matter when I add it to 0.20?
No, it's not going to affect within our significant figures, especially since we only have 2.
Exactly. So I'm going to get rid of that X. Okay. I'm going to make the assumption it's small, and I have a pretty good idea that's going to be true because my K value, which those two things have to ultimately end up producting out to, is a really tiny number. So it tells me that X is probably going to be a really tiny number. Okay. So what I can do if I take that out is this whole thing now becomes 0.20, get rid of that additive X, times the multiplicative X is equal to 1.1 times 10 to the minus 10th. Now, is that an easy problem to solve at this point? That's a whole lot easier than the quadratic, right? So now X is just equal to 1.1 times 10 to the minus 10th, okay, divided by 0.2. That's a whole lot easier, isn't it? If you work that out, that turns out to be, I believe, 5.5 times 10 to the minus 10th. All right, and that's a pretty darn small concentration. So at this point, I can go back up and ask, was I justified in throwing that additive X out? So if I have 0.20 and I add 5.5 times 10 to the minus 10th to that, okay, is that going to matter? No, can't matter at all. I mean, that's tiny. I mean, that's insignificant to the point of not worrying about it, right? So as was brought up before, you're only good to the hundredths place there, and 5.5 times 10 to the minus 10th goes way, way, way out beyond the hundredths place. We're talking about, 10th billionths place or something out, trillionths, I don't know, somewhere way the heck out there. Okay. So sometimes if I have a small value of K, I can make this kind of assumption and make the math a whole lot easier. Now, if you want to always get an exact answer, you can use the quadratic equation. That's perfectly fine. As a matter of fact, a lot of people have it already programmed into their TI calculators, and you just plug A, B, and C in, and it gives you the roots, and you pick the right one. That's perfectly okay. I know, for example, depending on who you have for a lecture, like if anybody got is Dr. Zaleski teaching the class this year? Anybody got him? So I know like Dr. Zaleski makes you quadratic it out every time, okay, which is fine. But if you have me and I'm not teaching it this year, that's fine if you want to do it. But if you can use the shortcut and get away with it, use the shortcut by all means, okay? That's perfectly okay to do. All right, so you'll find that depending on who your lecture professor is, some encourage that, some want an absolutely exact solution. I tend to like to simplify the math whenever possible because it just makes things a whole lot easier to do if I can get away with it. The trick is knowing when you can get away with it. So you always have to go back and kind of put the X back in and see if it makes sense. Okay? Does that make sense to everybody? So now here's the thing I want to look at. Notice my value of X. What does that X represent? It represents the sulfate ion concentration at equilibrium. So that's equal to 5.5 times 10 to the minus 10th. Whoops, 5.5 times 10 to the minus 10th molar. Okay, so look at that. What did we say that the concentration of the sulfate ion was if we didn't add the 0.2 molar barium? Well, we did that way up here. We said that it was 1.0 times 10 to the minus 5th, didn't we? So what effect did adding 0.2 molar barium to the overall solution have? Did it shift the equilibrium to the left like we predicted? Heck yeah, because now I've got 5 orders of magnitude less sulfate than I had before. So obviously I had to use up a lot of that sulfate in order to get the reaction to get back to equilibrium. Okay, that's Le Chatelier's principle. Now, why would this be important to us? Well, if this were, for example, our analytical reaction and we're forming a precipitate of barium sulfate that we're going to weigh out and quantitate from like we are in our lab tomorrow, okay, I'd want to make sure I'm getting as much sulfate into that precipitate as possible. So in that case, it would behoove me to add a whole bunch of the excess ion, the barium ion, to that to force that reaction back toward the precipitate as much as possible so I can capture as much of the sulfate as I possibly can, assuming the sulfate now is my analyte, the thing I actually care about, okay? So see how I can use the common ion effect, Le Chatelier's principle, to my advantage here to capture as much of the analyte in the precipitate as I possibly can. Again, I do it by adding a large excess of the excess reactant, which in this case would be the barium. Okay, so I can put Le Chatelier's principle to use here. Everybody see how I did it?
Yeah, I have a quick question. So whenever you're adding your barium, you get diminishing returns as you increase it more. Because if we look down at what eventually would become a quadratic equation, it means we're going to get diminishing returns. So where do we dictate how much barium should we add?
Well, that's a good question. And basically, the answer to it is enough that you're never going to see the value change in, say, the weighing of the precipitate. So in other words, you're right, you have diminishing returns. I could keep on adding barium as the excess reactant and getting more and more of the sulfate out of solution and into the precipitate. But at some point, I'm not going to be able to weigh the difference anymore, am I? In other words, I could keep adding that sulfate in, but it's coming in such small quantities that I'm not making enough extra precipitate to be able to differentiate to the 4th decimal place when I weigh it. Does that make sense?
Yeah, so basically you just got to exceed your significant figures.
You got it. That's basically what we're trying to do. So we're trying to tilt the reaction in our favor as much as possible, but there's no point in going too terribly far with it because it's going to make no difference to us in terms of our ability to make the measurement from a mass perspective. So that's basically the short answer. Does that make sense?
Yep.
Perfect. All right. Now, I think at this point, you guys have pretty much everything you need to be able to work all of the problems in the homework that I gave you last week. So that's another thing you can bring to me at lab tomorrow. Okay, so I think there are just a couple of equilibrium ones. And then there's a couple of KSP type problems in there. The last problem is a little interesting. Okay, I don't know if anybody's attempted it yet or not. Probably not because we've just now done KSP. But it kind of couches things in terms of forming the precipitate instead of dissociating it. So think about that as you set it up, okay? Think about it in terms of this example number 3. It's kind of sort of a common ion effect problem, all right? And the assumption when you form the precipitate, because I think it's asking you to determine what mass of precipitate you can make, is that's an easy bonding problem, isn't it? Because we always did it from the perspective of the limiting reactant and bonding. So really the question boils down to, is that a good assumption to make in that specific case? Okay, and it kind of comes down to the size of the KSP. So think about that. And if anybody's having trouble with that, catch me at office hours tomorrow and we can talk about it. But that's kind of a nice little thought problem for you guys to look at. I'm pretty sure that's the problem I stuck in there. I think I made it up, as a matter of fact. All right, any other questions before lab tomorrow? All right, that means I'll see you guys then. And it turns out we timed out just right. All right, guys, I am going to pop back into Zoom and stop the recording here, and I will see you